The common ion effect states that the presence of a common ion in solution decreases the solubility of the ionic compound. What that's basically saying is, normally I dissolve something in water. Yeah, I dissolve the ionic compound in water, which means that initially there are no ions in the water. We already said that earlier. Like when you fill out your ice table, the initial numbers are 0 and 0. Yeah, there is no common ion when I'm dissolving it in water because all there is in water is H2O. But like if I'm dissolving barium chloride in something that's not water, if I'm dissolving barium chloride in a solution that contains barium ions, which means I have the same ion, the barium ion is the common ion, then my solubility goes down. I can't dissolve as much of the solid that I put in. Or it might not be the barium. I'm dissolving barium chloride, but maybe I'm dissolving it in a solution containing chloride ion. Maybe there's no barium, okay? In which case the common ion then is chlorine, and I still can't dissolve as much of my solid. So let's say, for example, you're dissolving something in H2O. I'm going to clarify this a little bit more first. I'm dissolving something in H2O, and then I'm dissolving something in NaClAQ. And then I'm trying to dissolve barium chloride solid, okay? I'm dissolving barium chloride solid. So in terms of LCP, you can think about it a few different ways. I'm going to explain the LCP way first, and then we'll talk about it a different way, yeah? In H2O, the concentrations are 0, which means I shift that way. That's completely fine. In NaCl, though, it's sort of like you have some concentration of Cl minus. So like in LCP, right, you add something into the system and then it'll shift the other way to counteract that, okay? So when you add BaCl2 into a solution of NaCl, you already have some Cl minus in the solution. So because of that, the equilibrium is going to resist that a little bit. If you already have a lot of Cl minus in solution, the system doesn't want to put as much more into it because it's trying to resist that disturbance that you put in. So because of that, when you have a lot of Cl minus already in there, according to LCP, you'd shift the other way so that you don't make more Cl minus, in which case when you shift the other way, you make less ions. And if you make less ions, then the amount of ions that you have is by definition how much you have dissolved. So if you make less ions, then the molar solubility has decreased. Okay, so that's your LCP definition, LCP explanation for the common ion effect. The other explanation for the common ion effect is this. It's that at a particular temperature, KSP is specified, right? Because we know that if you change T, you change temperature, you change K. So then if I'm still at the same temperature, then KSP lets me know what's the maximum amount I can get dissolved. And this will apply really well to the final syllabus dot point that we'll talk about next lesson. Okay, so like KSP, regardless of what the actual numbers are, the expression is always this. Like this is always the expression. So then if the KSP is a particular number, I don't know what the particular number is. Let's make this up for now. Like, I don't know, 0.1234, da-da-da-da. Okay. That means that regardless of whatever is in the system, I only have a maximum concentration of the Ba2 plus and the Cl minus to make this particular number. Because it's like, regardless of whatever combination of this concentration, what this concentration is, I know that at this single temperature, it has to equal this number. Okay, can I get a thumbs up, guys? That makes sense to us. Temperature changes K. So if I keep temperature the same, K has to always be that number. K has to always be that number. I might clarify something in a second, James. K has to always be that number, which means, yeah, that I can only have a maximum amount of the two ions dissolved. Because if I get 1 times 4, let's change this number. If I get 1 times 4 and my K is equal to 4, then I can only get combinations of ions to get a K is equal to 4. I can never get like, 5 times 3 is equal to 15, because then that will be at a different temperature. So the only thing I can do is like 2 times 2 or 4 times 1 or something else, okay? My concentration of ions is capped at a particular temperature because K has to always be a particular number. Which means that when I dissolve something in a solution containing a common ion, I already have some concentration in there. Okay, so I'm approaching my maximum concentration before I even dissolved any of my solid, because my solution already has some of it. Which means that if my solution that I'm dissolving it in already has a little bit of it, I'm already approaching that maximum concentration I can make. So then it's like, oh, let's say my maximum concentration is 5 molar. Theoretically, let's say my maximum concentration is 5 molar. And in water, I'm allowed to dissolve up until 5 molar because my water doesn't contain any common ion. But then it's like, let's say I dissolve it in a solution containing a common ion. The common ion already has the first 2 molar. Okay, my solution already has the first 2 molar, which means when I put my solid in, my solid BaCl2, I can only dissolve enough solid to make the remaining 3 molar. I can't dissolve enough solid to make all 5 molar anymore. So to recap, guys, common ion effect, there is a cap. There's a maximum to how much concentration of ions you can have, because K has to be this particular number at this particular temperature. So if my solution already has some concentration, I'm already nearing my maximum concentration, so I have a shorter distance to get to my maximum concentration, which means I can't dissolve as much of my extra solid.